So in our last video, we got an introduction to what I call the local global heartbreak. This is what happens when we have an infinite collection of true statements that somehow fail to be a global truth when we try to mush them all together. Our signal example in the last video was this idea that the function f of x equals 1 over x is a bounded function on each one of the open sets that make up a cover of the half-open interval from 0 to 1 that includes 1 but doesn't include 0. It's bounded on this one, it's bounded on this one, it's bounded on this one, but somehow when we glue all of that boundedness together, even though the open sets on which this function is bounded cover the entirety of 0 to 1, the function is not in fact bounded on 0 to 1. So our goal is to try and make sure that that doesn't happen again. Can we look at statements which are quantified on a set which does not permit an infinite collection of truths to fail to glue together into a global truth? We're going to look at that in two different ways. And the first one in this video is going to be to look at sets that I call cover-finite sets. So what do I mean by a cover-finite set? Again, this is going to be some way for us to prevent falling victim to the local global heartbreak by examining more closely what it was about this previous example that made that heartbreak possible. So we had a function, f of x equals 1 over x, that is locally bounded in the sense that it's a bounded function on each one of the open sets that formed a cover of the half-open interval from 0 to 1, but failed to be globally bounded on the entire set from 0 to 1, inclusive of 1, exclusive of 0. So how was it possible in this example to be bounded on each one of these pieces, but not to be bounded on a subset of the union of all of those pieces? The problem seemed to be a problem about infinitude. Right? That we had these infinitely many different open intervals that were a part of our open cover for 0 to 1. And the problem seemed to be with this left-hand endpoint here at 0. This is where the reciprocal function kind of blows up to infinity, right? So this is the point where, as we get closer to that point, 1 over x really does fail to be bounded. It just crashes through every ceiling the closer that we get to 0. So the problem seemed to be that we needed infinitely many of these sets to get us close enough to 0 to be able to cover the entirety of the half-open interval from 0 to 1. Because of this funny open end at 0 on my interval from 0 to 1, we needed to have infinitely many of these sets in order to get all the way there. And the necessity of that infinitude appears to be the problem. We needed infinitely many of these open sets to be able to cover the entirety of 0 to 1 because of that open end at 0 to 1. So maybe the way to avoid the heartbreak in the future is to try to ensure that we never need to use infinitely many open sets to cover the set that we want to be interested in. And so this leads us to the idea of what we're going to call a cover-finite set. And when I say cover, what I mean is a collection of sets. And when we say open cover, we mean that those are open sets. So it's a collection of open sets such that if I union all those open sets together, that union contains my A as a subset. So we think of it like an infinite blanket, perhaps infinite, but a blanket of open sets that when we union them all together, they blanket my set A. So we call that an open cover. And we also have a term finite subcover. That's the result of taking only finitely many of the sets out of an open cover. It still gets to be what's called a finite subcover if only finitely many of the sets from that original collection can do the same job. Their union still contains A as a subset. So if we want to avoid the local to global heartbreak, one way of doing it might be to make sure that, again, we never need infinitely many open sets to cover A. Even if somebody gives us an infinite open cover, we would like for there always to be some finite subcover, some finite collection of that infinite cover that we can pull out, and that finite collection can do the same job of covering all of A. Such a set is going to be called cover-finite, or I call it a CF set. So a subset of the reals has the cover-finite property, and I'm going to call it a CF set. If any union of open sets which contains A as a subset need only involve finitely many of its sets. In other words, every open cover of A that you provide, I can, from that open cover, extract a finite subcover that still covers all of A. So CF sets are nice because we never need to use infinitely many open sets to cover them. Even when we try to use infinitely many sets to cover it, we only really need finitely many of them. So let's see if we can prove something about CF sets that can help us to understand what's going to be required of sets that we want to satisfy this property. So what we'll prove here is that CF sets are necessarily bounded sets in a metric space, so in particular in the real line. Right? So the idea for showing that every Cover-Finite, every CF set, is a bounded set is to imagine, if I have a CF set sitting right here, imagine just taking a successively larger but concentric collection of epsilon balls, epsilon neighborhoods. So we pick a point in K, and then we take an increasingly large sequence of epsilon balls around it, such that maybe we take the radii to be the sequence of ends. So we take the radius 1, then we take radius 2, then we take radius 3, etc., etc. Eventually, because every point in K is going to belong to one of those balls, we know that this infinite collection is going to necessarily be an open cover for this set. But if K is a CF set, that means that we don't need infinitely many of these balls to cover all of K. We only need a finite number to cover K. And because we only need a finite number, we'll be able to contain K within a single one of these epsilon balls, thereby proving that K is a bounded set. So to just write out those details, if K is a CF set, and I pick an arbitrary x inside of my set, so I guess we have to assume that K is non-empty. Clearly, if K is the empty set, then the empty set is bounded vacuously, so we don't have anything to do. So we pick a point inside of K, and then we take a sequence of epsilon balls around that point x. And that collection of balls of radius I for all natural numbers I starting from 1, that collection is going to be an open cover of my set. Again, because every single point of K is going to be some finite distance away from x, and therefore it's going to belong to the next largest integer radius epsilon ball. Right? So it definitely covers K, but it's an infinite collection of balls that it's taking to cover all of K. So we have an infinite collection that covers all of my set, but we've assumed that K is a CF set. It's a cover-finite set. It has this property that we never need to use infinitely many open sets to cover it. A finite subcollection, a finite subcover, will always suffice to do the same job. So by that assumption, there exists a finite subcover of this open cover of successively larger concentric epsilon balls. A finite subcover exists. And let's call the indices of that subcover the I1, I2, I3, up to the I-nth index of these sets. In other words, the balls of radius I1, I2, up through In centered at x. If we assume without loss of generality that my I sub k's are an increasing sequence, so this is my smallest one of my balls, this is the largest one of my epsilon neighborhoods, then the largest epsilon neighborhood, the largest ball, is going to contain all of the others because these balls are concentric. They're all centered around the same point x. And so the smaller ones are always a subset of the larger ones. So this union is just going to be equal to the largest one of those balls. And so what this tells me is that my entire set K is a subset of a single ball of radius I sub n, whatever is this largest index of my finite collection of epsilon balls. Therefore, every point of K is a distance of no more than I sub n away from x, and therefore all of my points of K are within a distance of I sub n plus the absolute value of x, distance away from the origin, the distance from 0, and therefore this set K is a bounded set, just by using the triangle inequality here. So cover finiteness is going to be our first idea for how to get around the local global heartbreak. We're never going to have that problem of an infinite collection of truths that are quantified on an open cover fail to glue together into a truth on the entire set. Because any open cover that you give me, it only takes me finitely many of those sets in that open cover to cover the entire set. And so I don't need to worry about an infinite collection of truths. I can worry only about a finite collection of truths that covers my set, and it is never a problem to take a finite collection of truths and glue them together into a single global truth. So this is the first really good idea for how we're going to avoid this heartbreak in the future. It's a little bit unwieldy to work with because working with collections of sets that could be possibly very largely infinite, right? Working with sets and covers and subcovers is sometimes challenging. So in the next video, we're going to look at an alternative framing, a different way to get around the local to global heartbreak using sequences instead of open sets. It's a little bit friendlier in some cases to use, but the great thing about it is having these two characterizations is going to let us deploy whichever one is easier in an argument later on down the line. So let's look at an alternative idea, the second idea, to avoid the local to global heartbreak next.